Welcome to episode 3.2 of the Explainer. You know, the main difference between a fuel injection system from 20 years ago and the C175's advanced high-pressure common rail setup basically comes down to one tiny, unglamorous component, the fuel control valve. It's just a simple two-pin connector receiving a pulsing electrical signal, but it's the single point of control over every single bar of pressure feeding 16 cylinders. Let's dive right in and see how we perfectly synchronize heavy iron with highly sensitive electronics. But before we get into the nuts and bolts of how it all works, we've got to anchor ourselves to the extreme reality of this engine. It generates 180,000 kilopascals. To put that into perspective, that translates to a staggering 26,000 psi of fuel pressure sitting in the fuel rail at full load. It is an incredibly hostile, volatile environment, and controlling it precisely in real time is absolutely crucial to hitting those emissions-compliant combustion targets. So here's our roadmap for today. 1. The Woodward high-pressure pump. 2. The fuel control valve. 3. The PWM control loop. 4. Diagnosing FCV duty cycle. And 5. Containing 26,000 psi. Okay, let's kick things off with Section 1, the Woodward high-pressure pump. Driven right off the engine's front gear train, this pump is basically the muscle of the whole operation. Whether you're working on the 16-cylinder or 20-cylinder configuration, the pump uses multiple internal plungers inside a barrel assembly to physically generate that massive 180,000 kilopascals required by the injectors. Fuel enters through an inlet check valve, gets smashed by the pistons riding on the drive shaft lobes, and is forced out into a common fuel passage. It's pure mechanical raw power. The pump is physically linked to the engine, spinning and always ready to build pressure. But here's the catch. If we just relied on a mechanical pump, we'd have a big problem. While it's fantastic at generating pressure, it's essentially a blunt instrument. It absolutely needs a brain at the low-pressure inlet to tame it, to meter the fuel and decide exactly how much is actually allowed to enter those high-pressure barrels in the first place. And that leads us perfectly into Section 2, the fuel control valve. This is the brain we were just talking about. This small L-series actuator from Woodward relies on a simple two-pin electrical connection to act as the absolute gatekeeper for the entire system. You've got this triangular opening that allows fuel to flow backward into the round opening to supply the plungers. When the ECM sends a signal, the passage opens up, metering fuel with incredible precision. If this valve closes, no fuel enters the pump and your rail pressure drops immediately. It literally controls the whole shebang. So how exactly does the ECM talk to this gatekeeper? Well, it uses a technique called pulse width modulation, or PWM. Basically, the ECM regulates the rail pressure by sending a PWM signal that shifts in real time as the engine load changes. By changing the duty cycle, which is just the percentage of time the signal is on during a single pulse, the ECM continuously varies the valve's effective opening. More on time means more fuel gets in to build up rail pressure. Less on time bleeds that pressure back down. Let's zoom out a bit for Section 3, the PWM control loop. The easiest way to wrap your head around this closed-loop environment is with a quick comparison. Think of an old mechanical regulator, like a manual dial on a furnace. Actually, scratch that. It's more like a blunt on-off switch. The modern fuel control valve, on the other hand, is like a smart home thermostat. It's constantly listening to the ECM's target pressure and making micro adjustments hundreds of times per second. So when a generator suddenly steps up its load, the rail pressure has to climb almost instantly. The FCV's PWM duty cycle shifts in real time to make that happen, all without a single moving mechanical link between the throttle demand and the fuel pressure itself. For the technicians out there pulling wrenches, here are your exact baseline operating specs. The PWM signal runs at a constant 500 Hz frequency. At low engine idle, you're looking at roughly a 10% duty cycle. As you ramp up to high engine idle, that jumps to about 25%. And at high speed with full load, your fuel actuator position command pegs right near 100%. Knowing these baselines is super important because when things deviate from these numbers, the engine is trying to tell you a hidden story. Let's decode that story in Section 4, Diagnosing FCV Duty Cycle. Let's run through a quick, real-world scenario. Say you're plugged in with Cat ET. You notice the FCV duty cycle is sitting unusually high while the engine is just idling, well above that 10% baseline we just talked about. But you check the rail pressure and it reads perfectly normal. So what exactly is happening here? Well, if the ECM is commanding a higher duty cycle, it means it's working the FCV harder just to maintain that normal pressure. The FCV isn't broken, it's just doing what it's told, and it's actually reporting a failure happening somewhere else. You should immediately suspect one of two culprits. Either you've got internal wear inside that Woodward high-pressure pump causing a loss of efficiency, or you have an open or leaking quilt tube bleeding off pressure somewhere in the rail system. Just think about that. You've just diagnosed a mechanical degradation using purely an electronic signal. But hey, let's pause for a second because the stakes here are literal life and death. Before you ever pull a pump or crack a line based on these diagnostics, you absolutely have to heed this warning. 26,000 psi fuel acts like a laser blade. It will easily penetrate skin and cause fatal injuries. You must complete the system bleed-down procedure using the Caterpillar electronic technician software before loosening any fitting. Never ever crack a line while the engine is running, and do not skip the electronic purge. Seriously, no shortcuts here. Which brings us to our final part, Section 5, containing 26,000 psi. Generating this massive pressure is one thing, but how do we move it safely? The answer is the double-wall quill tube assembly. If a bare, single-wall line failed, it would spray ultra-high-pressure fuel directly into a hot engine bay. Obviously, that's an immediate catastrophic fire hazard. So Caterpillar uses a double-wall design. The inner tube handles the high-pressure delivery to the injector with a metal-to-metal seal. The outer jacket acts as a secondary containment layer. If that inner O-ring seal ever degrades from vibration and starts to leak, the outer jacket catches the fuel and routes it to a dedicated, highly visible drain point right under cylinder 1. It turns an invisible, highly dangerous internal leak into a very obvious, manageable external sign. Brilliant, right? So we've mastered how this massive pressure is built by the Woodward pump, how it's precisely controlled by the FCV, and safely contained by the quill tube jacket. But here's the million-dollar question. How do you take a destructive 26,000 psi force and inject it directly into a combustion chamber without turning the entire engine into a literal bomb? Well, to figure that out, you'll just have to join me for our next explainer.